Hello. Oh, great. Okay. Yeah, I think so. I think I can talk. Okay.
So sorry, a bit late. So that let's start. This is welcome to the session of the GK based on GA1. Then so that we have to talk. The first talk is algebraic reductions of knowledge by Abhiram Kottapalli and Brian Parno. And Abhiram will give a talk. Please start.
Yeah. Thank you, Miyako, and thank you all for being here. Apologies for the delay. So in 1985, Goldwasser, Micali, and Rakoff introduced the notion of arguments of knowledge in a highly unconventional paper. And since we've developed better communication models and better time complexity and better succinctness and many other properties about these proof systems for the past 3 decades. But today, I want to share a new abstraction that we've been working on called reductions of knowledge, which capture a shifting perspective for how we view arguments today. Now, recall that an argument of knowledge is an interactive protocol between a prover and a verifier in which the prover proves that it knows a witness W for some statement U with respect to some relation R. And this relation could be something like 3-set or graph 3 coloring. And now the prover and the verifier talk, and eventually the verifier outputs true or false, depending on whether it believes the prover. But in the past 5 years, in search of practical efficiency, a growing body of works are beginning to describe interactions in which the verifier does not fully resolve the prover's statement to true or false, but rather reduces it to a simpler statement to be checked. Now, I want to tell you the story of this emerging paradigm in 3 parts. In the first part, I'll give you several examples of this interactive reduction, which at the outset won't immediately seem to be related in any way. In the second part, I'll offer reductions of knowledge as a unifying abstraction for this notion of an interactive reduction. And finally, in the third part, I'll aim to convince you that reductions of knowledge offer something more. You see, at this level of abstraction, we can state general results about how reductions can be composed. And as such, reductions of knowledge offer a minimal compositional framework for arguments of knowledge. Okay, so where have we seen interactive reductions before? Well, one of the defining examples is the recursive inner product argument. In 2016, Boodle, Cirilli, Chaitos, Garth, and Petit designed an inner product argument with only logarithmic communication overhead, which at the time was significantly better than what we knew was possible. And the way they did it was that instead of directly having the prover prove knowledge of a size and witness to the inner product relation directly to the verifier, instead, the prover and the verifier interacted using just constant communication to reduce the task of checking knowledge of a size n over 2 witness. That is, now it's a new half-sized instance witness pair. Now, naturally, you can see that if you take this protocol and you recursively compose it with itself a logarithmic number of times, you get the full argument for inner product. Now, it wasn't long before this idea started showing up in many other places. Just recently, at Crypto 2021, Bonnet, Drake, Fish, and Gabison observed that many modern arguments actually rely on having the verifier check several different evaluations of a polynomial, okay? So to make these sorts of arguments more efficient, they designed a new abstraction called a polynomial aggregation scheme, in which the prover and the verifier interactively reduce the task of checking several evaluations on this polynomial to a task of just checking a single evaluation on this polynomial. And just last year, here at Crypto 2022, we showed that it was possible for a prover and a verifier to interactively reduce the task of checking 2 statements in an NP-complete relation to the task of checking just a single statement in that NP-complete relation. And to formally define this protocol, we designed a new abstraction called holding schemes. This idea of an interactive reduction also shows up in places where you wouldn't immediately expect it. Just recently, Raffles and Zapico showed that many modern arguments reduce the task of checking R1CS, a popular characterization of NP, into the task of checking several smaller algebraic claims. And what they observed is that many arguments interactively reduce the task of checking an inner product, a Hadamard product, a task of checking that a vector was sampled correctly from a subspace. And there are many, many more examples of interactive reductions in literature, too many for me to go over today. But the point I want to make is that interactive reductions have become fundamental for describing the state of the art of arguments of knowledge. And this leads to the core problem of today. You see, while this notion of interactive reduction is universal, we still don't have a unifying theoretical foundation for them. And this makes it difficult to compose compatible techniques hidden under incompatible abstractions. So, in search of a unifying language, we formalize reductions of knowledge to capture this idea of an interactive reduction over statements of knowledge. And our core thesis for today is that reductions of knowledge serve as both a unifying abstraction and a compositional framework. So this leads into my second part, where I aim to relate to you what exactly a reduction of knowledge is. Now, just like an argument of knowledge, a reduction of knowledge is an interactive protocol between a prover and a verifier that reduces the task of checking a statement in a relation R1 to the task of checking a simpler statement in a simpler relation R2. Now, specifically what happens is the prover and the verifier take as input some statement, U1, and the prover takes as input a corresponding witness, W1, such that U1 and W1 satisfy the original relation R1. Now, just like an argument, the prover and the verifier interact, but eventually, the verifier outputs a new statement, U2, which it believes can be checked in place of the original statement, U1. And likewise, the prover outputs a corresponding witness, W2, which satisfies U2 with respect to the new relation, R2. Now, completeness holds if the prover has provided a satisfying witness, W1, then it must be the case that it outputs a satisfying witness, W2. And conversely, knowledge soundness holds if for any prover, even an adversarial prover, we have that if somehow it's able to output a satisfying witness W2, then it almost certainly must be the case that it knows a satisfying witness W1 for the initial statement. There's one thing which I'm sweeping under the rug here, which is what does it mean to know? And to properly define that, we can turn towards the standard arguments of knowledge literature. Specifically, suppose we have a prover that can talk to the verifier in such a way that it tricks it into outputting some U2 such that it knows a corresponding witness W2. Well, then for knowledge soundness to hold, we want specifically that there exists a corresponding extractor which can use this prover in a clever way, a rewinding or otherwise, to be able to pull out a witness for the initial statement U1. It turns out that when we formalize knowledge soundness in this way, a number of abstractions in the literature can be viewed as particular types of reductions of knowledge. Now, perhaps most interestingly, an argument of knowledge itself can be viewed as none other than a reduction of knowledge from a relation R into a canonical fixed relation RT representing truth. Specifically, RT will consist of a single instance witness pair. The string true is the instance, and the string triv is the witness. Now, in this argument, the prover and the verifier talk, and eventually, if the verifier believes the prover, it'll output the string true, for which the prover can output a satisfying witness triv. Now, otherwise, if the verifier does not believe the prover, it can output any other string, say false, for which the prover cannot output a satisfying witness. Now, it turns out that if you take the definitions of reductions of knowledge and you fix the latter relation to be RT, then you derive out the standard definitions for arguments of knowledge. Okay, so now I want to give you a concrete example of how we can use reductions of knowledge to study existing protocols. And we're going to start off again with the recursive inner product argument. So to properly start this off, I'm going to define the inner product relation. Okay, so the inner product relation is characterized by some vector length n. Okay, and the statement will consist of a vector of group elements of length n called G, and this can be viewed as a public key, and a commitment A bar in that group. Now, a witness is a length n vector of field elements called A, and this witness is satisfying. If you take the inner product of this witness against the public key, you get the commitment A bar. Now, in the language of reductions of knowledge, the original inner product argument, the original step, can be viewed as none other than a reduction of knowledge from the inner product relation over size n vectors to the inner product relation over size n over 2 vectors. Okay, so at a very high level, how this works is that the prover and the verifier start off with a satisfying instance witness pair. The prover computes several commitments based on its witness and sends it over to the verifier. The verifier then picks a random challenge R and sends it back to the prover. And then together they compute a new half-size commitment key by taking a random linear combination of the first and second half of the original commitment key. And we'll call this new commitment key G prime. Likewise, the prover computes a new half-size witness by taking a random linear combination of the first and second half of the original witness. And we'll call this new witness A prime. Now, together, homomorphically, the prover and the verifier now compute what they believe the expected new commitment A bar prime should be, okay, using the prover's commitments that is sent over to the verifier initially. And together, they output the new instance witness pair to be checked against the new relation, which is the inner product relation over size and over two vectors. Now, it turns out that if this latter relation, instance witness pair, is satisfying, then with very high probability, we have that the former instance witness pair is satisfying, okay? We can say this a little bit more formally with an extractor argument where we say, well, an extractor can use this prover, rewind it several times with different challenges for that R value, get different values for A prime as output from this prover, and then just interpolate back out the original witness A. Now, I want you to think about what it would look like if we were to try to prove the knowledge soundness of this protocol recursively composes itself enough times to build the entire argument for inner product. That is, suppose the verifier is composed with itself enough times to reduce all the way down to the inner product relation over size 1 vectors. And now suppose there exists some malicious prover simply to trick this verifier into outputting some statement in this relation such that it knows or it can output a corresponding satisfying witness. Well, to prove knowledge soundness, we need to show that there exists an extractor which can use this prover in a clever way to pull out the original witness, okay? And typically, how you would do this, traditionally at least, for arguments with several steps, is that you prove that there exists an extractor for each step, and you cleverly compose these extractors in such a way that you can build an extractor for the overall argument, okay? So in this particular case, what we will do is we'll build an extractor which just uses the last step of this prover, just rewinds that last step, and it interpolates back out a length 2 witness vector, which represents a satisfying witness if the verifier were to stop a step earlier, that is reduced down to length 2 vectors instead. Okay, well, what this extractor does is imply a corresponding prover that can trick this verifier that stops at length 2 vectors and tricks it into outputting some statement such that it can output a corresponding satisfying witness. Okay, well, now at this point, we can run the engine of recursion and we can say, well, this implies an extractor can pull out a size 4 vector and so on and so forth until eventually you get an extractor that can pull out the entire original witness vector of length n. Now, this is only a sketch of what the actual proof looks like, and to properly reason about extractors running extractors requires meticulous attention to detail. And this defies all intuition because it feels like it should be simpler to click together different steps of an argument. And this leads to the third part, where I aim to convince you that reductions in knowledge contain this flavor of complexity. In particular, the intuition that you can click together different steps of an argument can be stated precisely and proven in the language of reductions of knowledge. All the complexity of how extractors should be composed can be abstracted away into a single simple theorem that reductions of knowledge are sequentially composable. In particular, suppose you have a reduction of knowledge from relation R1 to relation R2, and suppose you had another one from R2 to R3. Then you can sequentially compose them in a natural way to derive a new reduction of knowledge from relation R1 to relation R3. Now, leveraging sequential composition, we can make the analysis of the original inner product argument significantly simpler. You see, all you have to do is prove that a single step is secure, and then you can just use our sequential composition theorem to layer on more steps and then prove that the entire argument is secure. And in our work, what we show is that we can generalize the original inner product argument to much more complex algebraic objects, such as matrices and tensors, and we can reduce them along any dimension, okay? And what we saw is that when we view the original inner product argument with this level of generality, a number of arguments or algebraic arguments in literature can be viewed as particular instantiations of this particular reduction of knowledge. And what this tells us is that a large number of techniques in the literature that we're using in practice today fill in our framework. And second, it tells that all these techniques enjoy the general composition guarantees that we provide. Okay, so now I want to pivot a little bit, and I want to talk a little bit more about how we can use reductions of knowledge to reason a little bit more abstractly. Okay, so to do that, I'm going to start off by defining an L folding scheme. Okay, an L folding scheme is a reduction of knowledge from L instances of a relation to a single instance of that relation. Now, recently, Ruffles and Zacharakis show that it's possible to bootstrap a two-folding scheme, that is, takes two instances, folds it down to a single instance, to build an L folding scheme. So specifically, suppose the prover and the verifier are presented with L instances to be checked. Well, what they could do is they could just run this two-folding scheme for each pair of instances to reduce down to L over 2 instances to be checked. They can repeat this again to reduce down to L over 4, and they can keep doing this and reduce all the way down into checking just a single instance. And thus, in a tree-like fashion, we've taken a two-folding scheme and bootstrapped it up to build an L folding scheme. Now, while this protocol can be stated quite simply, I want you to imagine what it would look like to prove the knowledge soundness of this protocol, which adds a whole new dimension of complexity. Now, we can't just directly use sequential composition like before, because we're composing a single protocol with two subprotocols. Okay, well, what you could do is you could break this apart into each layer, and then you can manually prove that each layer is a secure reduction from n instances to n over 2 instances. And then you can use sequential composition. But intuitively, it feels like you should be able to click together two arguments independently, side by side. And this is like, you should be secure automatically. There shouldn't have to be a fact that you have to keep reproving for each layer of this protocol. And this is precisely the intuition we capture in an additional parallel composition theorem, where we show that, well, suppose you have a reduction of knowledge from relation R1 to relation R2, and suppose you have another one from relation R3 to relation R4. Well, then you can parallelly compose them in the natural way to get a new reduction of knowledge from relation R1 and R3 to relation R2 and R4. Okay, well, leveraging parallel composition, we can state the original tree folding protocol in just a single line. And intuitively, what's going on is that, well, suppose you have inductively a reduction of knowledge from L over 2 instances to a single instance, which is an L over 2 folding scheme, okay? And you parallelly compose it with itself, you can do that, and get a reduction of knowledge from L instances to 2 instances. Okay? And then you can just invoke sequential composition to put it together with the original two folding protocol to reduce down to a single instance. Now, by the security of the sequential composition theorem and the parallel composition theorem, you have almost immediately, this is a secure L folding scheme. Now, so far, I've only really talked about how to reason more modularly about highly structured algebraic arguments. And while certainly reductions of knowledge do help in this scenario, in principle, we should be able to reason about any argument more modularly using the language of reductions of knowledge. And this is especially true for modern arguments for NP, such as Spartan, which can be viewed as putting together some of the best techniques of the past 3 decades to design some of the fastest proof systems that we know of today. And when we start viewing arguments in the language of reductions, we can start to build incredibly complex objects while ensuring that the soundness proofs remain tenable. And moreover, we can start swapping pieces in and out as we discover newer, better techniques. Now, with that said, I want to pull back up to our central claim for today, which is the reductions of knowledge serve as both a unifying abstraction and a compositional framework. And now this has 2 downstream effects. The first is that if you prove that your technique is a reduction of knowledge, then you know they will inherit general composition guarantees, and they will play nicely with a large class of algebraic techniques already shown inhabit our framework. And second, if you prove a general result about all reductions of knowledge, such as transformations or idealized models or impossibility results, then you know that your result will hold not only for arguments of knowledge, but also for a growing class of modern primitives. But even if you don't find yourself on either side of this abstraction, we hope that it affords a compelling new perspective, that proofs of knowledge can be viewed as maps between propositions of knowledge. Thank you.
Now, yes. Now is the time for the questions. If you have a question, so please come up to the microphone.
Hello. Yeah, thanks for a nice talk. I have a question about the compositional theorem. So for the composition theorem, is there like a bound on the number of compositions you take, or there's no, like what's kind of, like for the theorem holds for how many kind of compositions?
Yeah, that's a great question. So underneath the composition theorem, we have to run an extractor and another extractor. All that complexity of running extractors and extractors is abstracted away, right? So really, we can only do a constant number of compositions. And to do more than a constant number of compositions, you need to have stronger statements about how fast your extractor is with respect to the prover. Specifically, you want to say something like, oh, this extractor only has a multiplicative constant blowup over the prover, and then you can prove log depth and maybe other depths based on other guarantees based on the extractors.
I see. Yeah, thank you so much.
Yeah.
Are there any questions from audience? Okay, it seems not. So thanks to the Abhiham again. Okay, the second talk is correlation interactability on the snarks from sub-exponential DDH by Alkalai Chandri, Sanjam Garg, Abhishek Jain, and Suzo Jin, and Jen Sang. Then Alka will give a talk. Please
Yeah,
start.
thanks a lot for the introduction. I'm excited to talk about our work on snarks from DDH. As mentioned, this is joint work with Sanjam, Abhishek, Zheng Zhang, and Jia. So you've already heard a bit about snarks in this conference, and you'll hear a lot more today, but I'll still define what it is. So succinct non-interactive arguments or snarks is a protocol between Bob and a more computationally powerful Alice. Both of them have access to this Turing machine M and also an input X. So Bob wants to know if X on input to this Turing machine M accepts within T steps. Unfortunately, Bob doesn't have the computational resources to do the computation by themselves, so they want to delegate this computation to Alice. So the non-interactive nature ensures that Alice sends a single message to Bob to validate this claim. And unfortunately, while this is what we would want to hope for, there are some limitations in the so-called plain model. So we give both Alice and Bob access to the common reference string or the CRS. We further require that this proof is publicly verifiable to anyone with the CRS, not just Bob, anyone with the proof and the CRS can verify this proof. And the succinctness requirement is that the Bob should be able to verify this proof in time that's polylogarithmic in the number of steps. So the final aspect of this is the argument, which says that no computationally bounded cheating Alice can produce an accepting proof if the statement is false. In fact, we require something stronger, that this should hold even if Alice is allowed to pick the statement. So given this notion, it's natural to ask, what kind of languages can we hope to build this for? So let's start off being optimistic. Like, can we hope to do this for all of NP based on standard cryptographic assumptions? Unfortunately, this really wonderful work of Gentry and Wick showed that this is unlikely to happen under some notions of black box reductions. So we're going to sort of try to solve it for a subclass of NP, which we call snarks for batch NP or BOGs. And these are terms that I'll sort of be using interchangeably throughout this talk. So here, Alice wants to prove the validity of K SAT instances defined by the circuit C. And as before, we want it to be just a single message, publicly verifiable. Both Alice and Bob have access to the CRS. And the security property here is that no computationally bounded Alice, again, can produce an accepting proof if even one of the statements are false. So without any succinctness requirement, this is actually fairly trivial to achieve. Alice can just send over all the witnesses to Bob, and then Bob can verify. So for the succinctness, we require that the size of the proof is much smaller than sending over all K witnesses. And for the verification time, this is a little tricky to define because Bob at the very least has to read all the statements. So we say the verification time overhead after reading all the statements should only be polynomially dependent on the size of this proof. Okay, so we've seen that this is strictly a subclass of SNARKs for NP. So what are they actually useful for? So the original motivation was to construct SNARKs for all deterministic time computation, and this is something that we managed to do a couple of years ago. And despite their relatively short existence, bugs have given rise to a bunch of cool applications. And this is not all that's limited to. So these include things like verifiable PIR, incrementally verifiable computation, various notions of zero knowledge, aggregate signatures, and so on. And some of these you've actually already heard in this conference before. So okay, we have all these cool applications from bugs, so they seem like a useful primitive. What can we actually build them from? So we can actually build them from a few assumptions. The first is lattice-based assumptions like LWE, or assumptions over bilinear groups like DLIN, and also like a combination of two assumptions, which is sub-exponential DDH and quadratic residue. So given this, our work actually constructs these bugs based solely on the assumptions of sub-exponential DDH. So in particular, our theorem is that assuming the existence of, assuming the hardness of sub-exponential DDH, there exists SNARKs for batch NP, where the proof size goes logarithmically with the number of instances, k, and grows polynomially with the size of the circuit. And then we show the usefulness of this constructed box to show that we can construct SNARKs for all deterministic computation under the same assumptions. And here the proof size and verification time grow polylogarithmically in the number of steps. The only other SNARK that we know from DDH is this concurrent work of Kalai, Lombardi, and Vaikuntarathan, who show SNARKs for bounded depth computation assuming sub-exponential DDH. Cool. So given that we have these two results, due to time limitations, I'm going to mainly focus on the construction of bugs, and request you to see the paper for the other parts. So, but before I can really talk about the main tools and techniques, I do want to take a sort of meta view on our result, and this is something that has been following a bunch of recent work, which is construction of advanced primitives from DDH. So these are primitives like succinct secure computation, identity-based encryption, and more recently, non-interactive zero knowledge, which we knew from strong cryptographic assumptions, but have recently been shown to be possible just from DDH. So our result can also be viewed in this lens by saying that, the power of DDH is sufficient for constructing SNARKs. Cool. So now with that out of the way, let me tell you some of the core tools and techniques in our work. So one of the main techniques that we use is the Fierz-Shamir methodology, or the Fierz-Shamir transform. For those unaware, the Fierz-Shamir transform lets you start with an interactive protocol between a prover and a verifier, where the verifier just sends random bits and converts it into a non-interactive protocol in the CRS model, where the CRS consists of a hash. And the verifier's message is just simply replaced by hashing the transcript so far. So this protocol has been shown to be secure in the random oracle model, but since we're interested in standard cryptographic assumptions, how does one actually prove that this transformation is secure? So for this, we mainly care about statements that are false, and we don't want a cheating prover to prove false statements. So we define the set of what are called bad challenges. So verifier's challenge is set to be bad if the prover can come up with a third message that makes the verifier accept. So in the sort of interactive setting, the prover doesn't really have any control over how this challenge is picked by the verifier. Whereas in the non-interactive setting, it can choose different values of alpha, run the hash function over and over again, and try to get a challenge beta that falls into this bad set. So the requirement that we have is that for false statements, no cheating Alice can find an alpha such that the output of the hash is a bad challenge. And a hash function satisfying this is said to be correlation intractable for this specific set back. So to put it again in this picture, we have an interactive protocol that gives a certain set bad. Every protocol might give you a different bad set. And then we need to construct a correlation interactable or CI hash for this bad set to get a secure non-interactive protocol in the CRS model. So this is, in fact, the paradigm that was followed for the first construction of bugs, where you started with a special interactive protocol for batch NP to get snarks for batch NP. I want to briefly touch upon this special interactive protocol for batch NP. I'm not really going to talk about the properties or how you get from here to the snarks for batch NP. What I will say is that it does require computational assumptions. So in this work, since we want to construct these protocols just based on sub-exponential DDH, you actually require sub-exponential DDH for some of the primitives underlying this interactive protocol. And that's all I'll actually say about this interactive protocol in this talk. You can see the paper for details. So for the rest of the talk, I'm just going to imagine this to be some sort of magic box that gives the properties for bad, and we're just going to use it in that abstraction. Cool. So what are the kind of properties that this set bad has? And the properties that we're going to care about is that the set bad is product verifiable. So what does that mean? The first, it's a product set, meaning it's a sort of a parallel repetition of these bad sets that you see here at the bottom. And the verifiable, so even if the challenge set is polynomial size, that beta is sampled from a polynomial size challenge set, the number of bad challenges can be exponential in the total number of parallel repetitions. And the second aspect is that each of these bad sets can be efficiently verified. So given a beta, you can efficiently test whether it belongs to this bad set. Great. So what are the exact properties that this magic box gives us from bad? Specifically that it's a product verifiable set where the challenge space is polynomial size. And further, the product verifiability happens in TC0, and these are circuits that are of constant depth threshold gates. Cool. So now that we've got all the properties that we want from the magic box, we're going to ignore it from now on. So all that's left to do is construct correlation intractable hash functions for the bad satisfying these properties. So we do actually know correlation intractable hash functions from sub-exponential DDH. This is based on work by Jen and Jin, but they don't quite get what we already want. They get something that's sort of related. So they get correlation intractability for bad sets that are computable in TC0. Remember, I said verifiable TC0 is something that we had. This is computable in TC0, meaning that if the bad set just has a single element, you can actually find this element in TC0, not just verify it. So the main question then remains, how do you get from correlation interactability of this computable set to correlation interactability of the set that you really care about? So unfortunately, there's some difficulty in going from computability to this set here. And this mainly comes from the fact that these bad challenges are a product set. And you, as I've already mentioned, that you can have exponentially many bad challenges. So this was observed in this work of Holmgren, Lombardi, and Rothblum. And it's basically that you can't do tricks like randomly guessing the bad challenge because there's just too many of them. Cool. So the rest of my talk is mainly going to be focused on sort of some high-level ideas of how we get from correlation intractability of computable sets to the bad set that we care about. So for this talk, I'm actually going to make an even more simplifying assumption. I'm going to ignore the threshold aspect of the circuits altogether. I'm just going to say, these are poly circuits. The threshold aspects are sort of secondary and are dealt with in the paper. Cool. So let's start out with the warm-up case. We want to say that given a bad set, we can actually compute the elements of this bad set. So let's start off with the verifiable bad set, but this verifiable bad set has a unique challenge. Can we actually compute the unique challenge for this set? It turns out yes. And this is simply a brute force. We iterate over all elements in this challenge space and check if it's bad. The fact that the challenge space is polynomial size and bad is efficiently verifiable means that you can actually compute efficiently this bad challenge. All right. So does this extend to sort of the product relation or the parallel relation? And it does in pretty much the same manner as you would expect. You sort of do this in parallel for each of them. So as long as there are polynomially many repetitions, this process of finding the bad challenge still remains efficient. Cool. So we've sort of gotten halfway there. We've gone from showing that some correlation intractability for things that are computable to correlation intractability for things that are unique and verifiable. It's not quite what we want yet. So for the last part of the talk, I'm actually going to show you how you can reduce, for the simpler case of no parallel repetition, just one bad set, but without any restriction on the number of bad challenges, we're going to reduce this to the case of verifiable unique bad challenge. So the main idea is to view challenges that you get as bits. So here it's going to be represented as L bits. And view is generation via segments. So we have K segments, and each segment has L by K bits. And the challenge is going to be generated one segment at a time. So what do I mean? So I have, this is what I want to get to. So I generate the first segment, which is this blue bit. And now I generate the green bit. And now you must be asking, I mean, if you're just doing this, why didn't we just do it all together in the first place? And for that, it's because in the non-interactive setting, the way that we're actually going to generate them is hashing the prefix of the random string. So here you can see the green segment is actually a hash of the blue segment. And further, the hash function that we're going to use is a hash function that's going to be correlation intractable for these efficiently verifiable unique bad challenges, the things that we've already learned that we can handle. So you can do this for sort of the other segments, and that's how you generate a random challenge. Okay, now that we know how to generate random challenges via segments, we need to see what the usefulness of actually dividing it into segments is. So for each segment, we want to say that a segment is good or bad. And so we're going to define corresponding sets for each of these segments. So these sets are going to be different for each segment. And these sets are going to have to satisfy two properties. The first is sort of something obvious that, that's what I've been building towards, is that these have to be efficiently verifiable and unique. So that's our first property. And the second, for this to even be useful, we want to say that if there is a challenge on the left that's bad, then there must exist a bad segment on the right. Cool. So let's see how one defines these bad segments. So these are the segments that I have here. There are 4 segments. And for this illustration, I'm going to think of each segment as just containing a single bit. And this sort of naturally generalizes to the setting of more bits. So the challenge space here is this entire white space. And the bad challenges for the original bad relation are this dark set in the middle. So now that once we are sampling the first segment, it divides the challenge space into 2, which is the top half and the bottom half, depending on what prefix you choose, 0 or 1. And we say, intuitively, we say a challenge is bad if with that prefix, the number of bad challenges that remain are more than half of the original bad challenge. So from the picture, it should be fairly obvious that the bottom half has more bad challenges than the top half. So the bad segment is indeed the segment that corresponds to the bit 1. So a couple of comments to note. And by pigeonhole principle, there is only ever going to be one unique bad segment. And this is true even if the segments are more than 1 bit. And the second is that by observations that we have already made, this can actually be efficiently verified in polynomial time. Cool. So this is how we decide if the first segment is bad or not. What about the second segment? So let's say we've picked the first segment to be 0. That's the top half of the challenge space. Now we want to pick the second segment. And as before, we partition the remaining challenge space into 2 halves, the left half and the right half, depending on the prefix. And now we say the green segment is bad, given that the first segment blue was 0. If, again, the remaining bad challenges are at least half of the total challenges. So again, from the picture, you can see that there are more bad challenges in the left half than the right half. So that's our bad segment. Cool. So we defined what these bad segments are, and I defined it only for 2 segments, but you can define it in the same way for all of them. And we've already described just by defining the properties that these are actually efficiently verifiable and have only a unique bad segment. And the last thing I need to show is that if the challenge on the left is bad, there must exist a bad segment. And this is simply a matter of contradiction. Let's say I do want to generate a bad challenge. And let's say the number of segments that I pick are k, such that 2 to the k is larger than the total number of bad challenges. So when I start off with my challenge space, I have t bad challenges. If I pick a good segment, the number of bad challenges that remain are fewer than t by 2. If I do this again, it's fewer than t by 4. And after k steps, I'm left in the setting where I have fewer than 1 bad challenge. But this is a contradiction because I've assumed that I'm going to end up picking a bad challenge. So it must be the case that if I have to pick a bad challenge, that at least one of the segments that I pick must be bad. And this is basically the main idea. So at least for the case of no parallel repetition, I've shown you how you get from things that are computable to things that are verifiable and unique, and things that are simply verifiable. And that's pretty much all I'll have to cover. I just want to make some concluding remarks. In the paper, obviously, we extend this to the case of parallel repetition. The choice of parameters for things like the size of segment and the number of repetitions are actually quite crucial. And for the thing that I've sort of swept on the rug, which is the magic box, we actually construct a new and interesting somewhere extractable hash scheme based on sub-exponential DDH. So just to recap our result, based on sub-exponential DDH, we construct snogs for batch NP and P. And that's all I'll have to talk about today. Thank you.
Any questions? Please come to the microphone.
Okay, I have a very basic question. At one point, you were saying that the challenge, one of the problems is that there are exponentially many bad challenges. But then you were saying the challenge space is of polynomial size.
Yeah. So this comes from the fact that you have product relations. So in each challenge space is polynomial. So say think of them as only being 2 bad challenges in this challenge space. Now, if you repeat it t times, the number of bad challenges become 2 to the t. So your challenge space overall is exponential, but at each individual thing, it's only polynomial. And the searching that you're doing is only for 1 repetition at a time.
I see. That makes sense. Thanks.
Yeah, cool.
Hi, thanks. Just a quick question. So maybe you said it and I missed it. So about the group that you can use for DDH, do you have some constraints on it? So with respect to computability in TC0, so can you do, I don't know if it's TC0 that
It's
matters.
not for TC0, it's for, the parameters translate to the kind of groups that we believe
So elliptic
DDH
curves
is-
will work. So for
Sorry?
elliptic curves will work.
I
Okay.
think so, yeah.
Okay.
It's the DDH, the assumption we need is that it's both hard against sub-exponential time adversaries, and you only get a sub-exponential advantage. So it's a
I see.
strong assumption.
But there are no constraints on how efficiently computable the group operations are in order.
Poly.
Okay. Okay, thanks.
Thanks.
Are there any more questions? And I can't see the questions from the Zoom audience. So let's thanks to the again.
Thank you.
Now is a coffee break. Then so please come back to the 10:20.